Now we'll work through some sample problems and finish out the unit from pages 87 to 92. So at the top of page 87 is example 19.26, which states that you have a reversible reaction at 450 Kelvin and a delta H of 34.5 kilojoules. Calculate the delta S. First of all, it's a reversible reaction, which is telling you that it is at equilibrium. This means your delta G has to be equal to 0. Therefore, the equation delta G equals delta H minus T delta S can actually be written as 0 equals delta H minus T delta S. So we have a temperature and we have a delta H, but we don't have the delta S. So this is what we're solving for. So I'll go ahead and rearrange the equation and set it to solve for the delta S. Subtract both sides by the delta H. And so that'll give me negative delta H is equal to negative T delta S. And now I'll divide both sides by negative T. These two will cancel and become positive, so delta H divided by the temperature will be equal to the delta S. Keep in mind that delta S is typically reported in a unit of joules, so I'm going to have to convert my delta H from kilojoules to joules. So let's go ahead and plug in our values. 34.5 kilojoules, and 1 kilojoule is equal to 1,000 joules, and that's going to be divided by the temperature, which is 450 Kelvin. And so when we do this math, we get a delta S equals 78.7 joules per Kelvin. We can actually check and make sure that this is the right answer by plugging in our delta S, our delta H, and our temperature into our equation, and we should equal 0 once we do the math between those. Example 19.27. A reaction mixture with 1 molar concentrations of reactions and products is spontaneous at 450 Kelvin. Delta H of formation is 34.5 kilojoules and delta S is 85 joules per Kelvin. Assuming that your delta H and your delta S do not change with temperature, calculate the temperature where the reaction will no longer be spontaneous. So there are several things we have to consider with this. First of all, it's spontaneous at 450 Kelvin, and I've been told I have a delta H of positive 34.5 kilojoules, a delta S of 85 joules per Kelvin. I've been asked, what is the temperature? However, you need to consider the temperature when it's no longer spontaneous. And remember, we're kind of thinking in the forward direction. So if it were spontaneous in the forward direction, you would have a delta G that is negative in value. However, we want to know when will it no longer be spontaneous in the forward direction, and so that would mean we would want to know when will it have a delta G that has a positive value or is greater than 0. So we'll use this idea in the equation delta H minus T delta S, and all of this should be greater than 0, because remember that delta G is equal to delta H minus T delta S. And so I will just sub all that in for my delta G, and all of that should be greater than 0, and that's when the reaction would no longer be spontaneous. So now I'm going to be solving for the temperature at which this occurs. So let's go ahead and rearrange this equation and set it to solve for T. First, I'm going to subtract delta H from both sides of the equation, and so we'll get negative T delta S is greater than negative delta H. Now, I'm still solving for the temperature, so I'm going to divide both sides by negative delta S, divided by negative delta S. Be careful, because when you're dealing with an inequality, if you divide or multiply by a negative, then it causes the inequality to reverse. And so this is all going to cancel, and my negatives will cancel, and I have to reverse this sign. So it's really going to be the temperature is less than the value of delta H divided by the value of delta S. So now I can plug in my numbers. T is less than, we'll have 34.5. Remember, this is in kilojoules, and I'm going to go ahead and change this to joules. And you can do it either way. You can change your delta S to kilojoules if you want. So this is going to be in joules, and then I'll divide that by the delta S, which is already in joules, 85 joules per Kelvin. And when we do this math, we get a temperature that is less than 405.9 Kelvin, is when this reaction will no longer be spontaneous in the forward direction. Example 19.28, we want to find the normal boiling point for carbon tetrachloride if we're given the delta H of formation values and the S of formation values. So first let's write an equation for this. The boiling point means it's going to change from liquid to gas. So we'll have carbon tetrachloride as a liquid convert to carbon tetrachloride as a gas. We're going to need an equation so that we can determine the delta H of reaction using the formation values and the S of reaction using the formation values. So let's go ahead and do that. The delta H of reaction is going to be equal to the delta H of formation of the products, which is negative 106.7, minus the delta H of formation of the reactants, which is negative 139.3. These become positive, and when we do this math, we get 32.6, and it's in kilojoules per mole. We'll just write kilojoules. Now let's find the S of reaction. We're going to take the entropy of the products, which is 309.4. This is joules, says so here, minus the entropy of the reactants, which is 214.4 joules. This is going to give us 95 joules, and we're going to go ahead and convert this to kilojoules so that it matches our delta H. So we'll divide by 1,000, and that'll give us 0.095 kilojoules for our entropy. So now that I have this information, keep in mind that we're asked to find the normal boiling point, which means what is the temperature going to be when this boils? When it is at its boiling point, it's going to be at equilibrium, which tells you that the delta G is going to be equal to 0. And so we can write our equation as 0 equals the delta H minus the T delta S. Now, I want to solve for temperature, so I'm going to subtract delta H from both sides of the equation, and that'll give me negative delta H is equal to negative T delta S. We'll divide both sides by negative delta S, and these are going to become positive, and so my temperature is going to be equal to the delta H divided by the delta S. And so I'll plug in my values, 32.6 kilojoules divided by 0.095 kilojoules, and this gives you a value of 343.16 Kelvin is the normal boiling point of carbon tetrachloride. Example 19.29 is in the review section. So here's our equation, and the question is, what is the delta S of the system, the delta S of the surroundings, and the delta S total? We're told, first of all, that we have a liquid changing to a solid, and it's at a temperature of negative 5 degrees Celsius and 1 atmosphere. Remember that the normal boiling point, the normal freezing point of water is 0 degrees Celsius, and this is well below 0 degrees Celsius. So it's past the freezing point, and so it's definitely spontaneously forming a solid at this point. So we know that our delta S total has to be positive or greater than 0 because the forward reaction is spontaneous based on the temperature that we're given. Secondly, we're changing from a liquid to a solid. That means it's becoming more organized or more orderly. And so my system is, the entropy is decreasing. It's becoming more ordered. The delta H of the surroundings, so here's my system, and in order to change from a liquid to a solid, the liquid is going to have to release heat. And so this is an exothermic process. And so because it's exothermic, the delta S of the surroundings is positive, and so this is going to be greater than 0. This should make sense because the delta S total must be greater than 0, which means your delta S plus the delta S of surroundings together should be greater than 0, and since this has a negative value, this must have a tremendous positive value. Our final example is 19.30, and we're given liquid nitrogen has a normal boiling point of 77 Kelvin. Determine the signs of the delta S for the system, the delta S for the surroundings, and the delta S total for this process. So if we were looking at a boiling point graph, here's where it's a liquid, here is where it's boiling, and then here it's where it's a gas. And this temperature right here should be 77 Kelvin. However, we're given a temperature of 70 Kelvin, so it's below the boiling point. And so we can tell with that fact that the forward direction is not spontaneous at 70 Kelvin. It would be spontaneous if we were at 77, and even more so if we were above 77 Kelvin. So since it's not spontaneous in the forward direction, we're going to say the delta S total is less than 0 or a negative value. Now, a liquid changing to a gas, that's my system, and a liquid changing to a gas is going to become more disorderly, more disorganized, more spread out. And so the entropy of the system is increasing, becoming positive. Finally, when we change phase from a liquid to a gas, it has to absorb heat from the surroundings or be endothermic in order to do this. So the delta S of the surroundings is going to be less than 0 or negative in value.